Good morning, students. Today we will continue to finish up our lecture material, and then you probably can start trying out the tutorial questions, okay? Because we have gone through the Gauss-Jordan elimination method already, so there are some questions in the first tutorial that test you on this thing, okay? But today we are going to be more focused on interpreting the solution forms. So far we have only looked at the unique solution, right? So unique solution means, for example, you got two equations, two unknowns, then you solve xy, right? Two unknowns xy, two equations, you can get unique solution. So what are unique solution? Unique solution are just unique values associated with each variable. Okay, so effectively it is trying to define or find out what is the intersection space between the geometries where each geometry is represented by one equation. So in this exercise we have seen that you actually have three geometries, right? Three planes in fact. Okay, so therefore the solution that satisfies all three planes must logically be the intersection point on all three planes. Okay, that means the point that is common, right, is common on all three planes. Okay, so therefore that point, as we have solved using this elimination method, is x equals to 2, y equals to -1, and z equals to 1. Okay, yeah, so that's the thing about unique solution. And today we are going to see the other two types of solutions that can occur. Okay, and whether you, okay, what kind of solution you get, okay, when you have many equations, right, like 3, 4, 5 or more, right, you will not be able to identify the type of solution so easily. Okay, so of course if I give you two solutions, if I give you two equations, right? Let's say for example, two equations shown here. Now, you can pretty easily tell if the two lines are parallel. Okay, I'll give you an example here first. Okay, that's an intuition, right? Before we jump into the thing. Okay, now, you want to get a point. How is it possible that you can get a point? Well, the two lines cannot be parallel. Right, because non-parallel lines on the 2D plane, they inevitably will intersect. Okay, so as long as the two lines not parallel, we will get a unique solution. Okay, that's very clear because we get an intersection point, right? A point is a coordinate, x is a particular coordinate, y is a particular coordinate. Now, if the two lines are parallel, so how do I know if the two lines are parallel? Well, the gradient is the same for the two equations. Okay, so for example, you can see that this is 2x plus 3y, right? So if you isolate y, you're going to get a minus 2/3 x. Okay, minus 2/3 x. Now, if the coefficient for x and the coefficient for y here happens to be such that you get the same gradient of minus 2/3, then the second line is parallel to the first line. You get that, right? Okay, so for example, let's say it is 2, 3. If I put, for example, 4, 6, that means 4x plus 6y. 4, 6, the ratio, right, is the same as 2, 3, the ratio. So therefore, if let's say this guy is 4, 6, 4x plus 6y, you can be assured that this line, the second line, will be parallel to the first line. So if two lines are parallel, just by looking at the equations and their coefficients, right, I can tell that there is no solution. There is possibly no solution because two lines cannot intersect. What? Cannot intersect, then where is the intersection space? There's no such thing as an intersection space. So therefore, this is easy to see. However, when I give you three equations that involves planes and four equations, for example, that involves 4D geometry that we cannot imagine, then it is not easy to tell at all. Okay, what kind of solution you get? Is it no solution? Is it a point? Or is it other kinds of solutions? Okay, and this is where the Gauss-Jordan elimination will come in. More specifically, the row echelon form. The row echelon form. Okay, because how we get to the row echelon form is such that we perform our row elimination, row operations. Okay, so you can see we make 0, and all that, right? Then after that, you notice that we get our row echelon form here. So in fact, this guy is the row echelon form. So I got some questions after the lesson on Monday, and that is right, pretty much concerns everybody, right, in terms of the assessments. Will I strictly demand that you perform the row ops until the identity matrix here? The answer is probably no. Okay, probably no, because actually, if you can perform row ops, whether you do to the row echelon form and you do back substitution, or you prefer to do it until the identity matrix here and read off the answers on the right hand side, I will leave it up to you. Okay, because I think some of you seems to be not very comfortable with getting the upper triangle of zeros, like this upper triangle of zeros. Effectively, it's actually the same stuff. It's just like a mirror image. Okay, so if you want to make the 3 zeros here, you can see the 3 zeros here, you perform the row ops. Then after you want to get the upper 3 zeros here, then you just perform the similar row ops. Okay, of course the row ops is not the same lah, right? Exactly, it's not the same, but it's just that whatever you do, right, to get the 3 zeros here, that's the point here. Okay, so whether you go to I, V, or you go to the row echelon form and perform back substitution is up to your preference. Good question. The answer is yes. There will be, okay, so what's the deal with getting the identity here? The deal with getting the identity here, right, is such that this method also extends itself to getting the inverse of a matrix. Okay, so this one will be covered in topic 2. This one is a matrix A, right? So if I want to get the inverse of matrix A, right, I can perform row ops until, right, I will get an A inverse here. Okay, but if I were to get an A inverse here, then this guy got to be I. Right, so this will be demonstrated in the second topic. Okay, but this is not the only way to get the inverse of a matrix. Right, there is another so-called more efficient way. Okay, so you might get tested, you might, right, such that you have to perform the row ops from this A/B to I/V. Okay, but solving of linear equations wise, I think I will not restrict you. Okay, you can do this or you can do this, is perfectly fine. Okay, and then just want to make a note here before we continue the lesson, or we start the lesson for today, and that is, right, I forgot to mention that, or I forgot to wrote down that, now you see, after you make these 2 zeros, right, after you perform the row ops, right, to get rid of the 2 to become 0, you make use of row 1, so you get R2, row 2, minus 2 times row 1, right? Okay, so you get 2 minus 2, you get a 0 here. Okay, now, after you have made the 2 zeros in the first column, you want to make 0 for the second column. Okay, this guy. When you make the 0 for this minus 2 term, this element, right, you do not use row 1, you know. Because if you were to use row 1, then you get 0 minus some multiple times 1, right? You're going to get back this entry. So therefore, here, do not use row 1. Okay, or else undo the first 0. Okay, so this is, I mentioned this during the last class, but I didn't write it down. So I think I better write it down to reinforce this. Okay, and of course you will find out yourself the hard way lah, right? If you go and use row 1 here, then you realize that, hey, this one pop back already. Correct or not? This minus 2, let's say it becomes 0, then this thing will come back. This thing will become like minus 3 or something, for example. Then this one come back already, then you need to make this 0, then you ding dong, cannot be what? Correct or not? So therefore, you should understand that after we make the first 2 0, you have to use row 2, right? You have to use row 2, you can see here. Right? You use row 2. so that the 0 here, the 0 here will not affect this 0. The 0 here will not affect this 0 after you perform the row ops if you were to use row 2. Okay? So if I give you 4 by 4 matrix, you should know what to do. Okay? So now we talk about the linear independence and type of solutions. Okay, so what is the meaning of linear independence? Now, the fancy terminology, right, is defined by this equation. But this equation is too fancy. Okay, so I'm going to tell you the layman understanding first, right, before we look at the fancy equation. Okay, so what's linear independence? Now, remember, every equation in the system of linear equation is representing a geometry, a line, a plane, or whatever. Okay, it can be 4D, 5D geometry as long as the equation is linear. Okay. Now, linear independence means one geometry is not dependent on other geometries. Okay, so what does that mean? That means I cannot take, for example, these two equations. I cannot take these two equations because each of them represents a plane, right? Why not? I cannot take this plane, add or subtract a multiple of this plane to get the first plane. I repeat that again. I cannot take this plane, okay, add or subtract another plane to get the first plane. And of course, vice versa. That means I cannot do that, right, for any of the planes here. Okay? So this also means that each plane is independent of other planes. Okay, that means let's say this plane 1, this is plane 1, this is plane 1. So in order to get plane 1, it must be defined separately. I cannot possibly take plane 2 and plane 3, manipulate them, right, add them up, subtract or whatever, right, to get another plane. Okay, if you have a plane that is a linear combination of any of the two planes, that means effectively you don't have a third linearly independent plane or a third linearly independent equation. Okay? Right? Can? So therefore, this is the meaning. Then, actually, the meaning is, I would say, easier to visualize because planes may be a little bit difficult to visualize. Okay? So if you have like two lines, imagine, of course, two lines will be quite, simplistic. Okay, let's say you have this first equation. Okay, let's say this is not my second equation. Not my second equation. So now I give you another equation. Okay, let's say I go and take minus 1 multiplied by this equation. So therefore, minus 1 multiplied by this equation, I will get minus x minus 3y, minus x, minus 2x minus 3y equals to minus 1. Okay, so you can see that this second plane is just minus 1 multiplied by this row. So let me call this row 1. Okay, minus 1 of row 1. Minus 1 times row 1. Okay, now if I take a multiple, it means a constant, right? Doesn't need to be an integer. Okay, it can be any number. I go and multiply by this row 1. Then I define this as my second geometry or second line. Now in this case, because the first, or rather this equation depends on row 1, right? It is just a multiple times the row 1. So therefore, this is not linearly independent to row 1. Is that alright? Can? So therefore, yes. No, it's not. It's the same equation. In fact, I can multiply by any number. So for example, if I take this, right, multiply by, let's say, 1/3. If I multiply by 1/3, right, then you notice that you get 2/3 x plus y equals to 1/3. Now, this 2/3 x plus y equals to 1/3 is going to be exactly the same line as this. Exactly the same. If you were to plot it out, in Desmos or any graph plotter, right, you realize that this equation will give you the same exact line as this equation, which is the green line. No separation at all. Okay? So what does that imply? Now that implies that you have repeated geometries. Actually, it seems that the two geometries are different, but actually, in essence, they are the same. Okay? So when that happens, you will not have a unique solution. Okay? Why? Because the line intersects with itself. If the line intersects with itself, how can it give you a point? Agree or not? Right? This green line intersects with another green line. It's the same line, what? So what's the intersection space? The intersection space is the whole line itself. Okay? So therefore, this is what happens when you have no linear independence. You do not have linear independence. Yes?
What do you mean by space? Is it like a range or?
Intersection space is what is the intersection geometry. So if you get a unique point, like this guy, unique point, then there is an intersection point. Okay? But if you get an intersection that is comprised of a continuum of points, like the whole line intersect with itself, then the intersection space is a line. Agree? Okay? But there could also be no intersection space, as demonstrated earlier. No intersection space means no solution. Okay? So, of course, not to worry, later we'll look at more examples. Okay, so in essence, there are three types of solutions. One is unique solution. The other one is no solution. Then the third one is infinite solutions. Okay, so which, in what scenario will you get which, right? Later on, you will see that the row operations or the Gaussian elimination will review. Okay, but now let's look at the equation definition of linear independence. Okay, so this is actually similar to what I explained earlier on, right? That is, right, if you have all the rows multiplied by a constant, so this K1, K2, Km, right, all constants. Okay, it can be minus 1/3, 1, 2, cannot be 0 lah, okay, all constants. Now, you take a constant, multiply by each equation, each row. Then you sum to the other rows. Repeat this procedure. Now, if you can get 0 here, right? If you can get 0, that means because it's possible that you get like this K1 times maybe x, right? Let's say K1 is minus 2x. Let's say minus 2x, then maybe this is a plus 2x. That means K2 is 2, for example. Okay? So you can get like minus 2x plus 2x, then the x terms cancel. Okay? So therefore it can be said equally for the y, for the z, whatever. And if you can get 0 here, that means the rows are not fully linearly independent. That means there is, like, for example, one row, right, that is dependent on other rows. That means one row that can be formed by other rows. Okay? Now, what is linearly independent? Linearly independent means you can only get 0 on the right-hand side if and only if your k values are all 0. You get that right? Okay? If you can get 0 here, only if all k's are 0, that means row 1 is not formed by a linear combination of other rows. Same thing go for row 2. Same thing go for row 3. Same thing go for until the last row. Can okay? So therefore, this condition is an equation that is difficult to check. Okay, it's very difficult to check because how are you going to solve for the K1 to Km, right? Especially you have one equation, I mean, it's so many, if you have many rows, right, then it's not possible to check. Therefore, we will make use of the row echelon form. Okay, the row echelon form. So you can see that, right, it says here, if there are no rows with all zeros in the row echelon form of the coefficient matrix, right, then all equations in the system of linear equations are linearly independent. Okay, so we're going to look at our previous example. Okay, of course, we know that this is a unique solution, right? Unique solution is a point of intersection. And you can see the row echelon form is here, right? Now, you notice that in all three rows, after you get the row echelon form, you do not get a row with all zeros. If you get a row with all zeros, that means this guy is a 0, this guy is a 0, and this guy is a 0. It's possible. Okay, later on you'll see an example, right? It's possible. After you do row ops, right, you try to eliminate, right, try to get 0 here, right, then you notice that, hey, this is also 0. Now when this happens, it means you only have 2 independent rows instead of 3. Meaning to say one of the equation is linearly dependent on the other 2. It's not linearly independent. When that happens, actually you have only 2 planes. Okay, effectively you have only 2 planes, not 3 planes, only 2 planes. So what is the intersection space of 2 planes? A line. You take 2 planes, right? Let's say this plane, 1 plane, right? You intersect. You notice that the intersection space is a line. Okay? So when that happens, right, you are going to get infinite solutions. Because a line, right, is infinite solutions, right? Because it's a continuum of points, so-called. Okay? Yes. Yes. You can manipulate any of the 2 to become the third one. Meaning say a linear combination of the other 2, right, will give you the third one. Okay, later on I'll give you some more examples. Right. Okay, so let's first of all recap on the solution types first. Okay, so this one, unique solution, is very easy lah. Okay, this occurs when all equations are linearly independent. Right. So therefore they intersect solidly, uniquely at a point. Okay, so this system, as long as you have solutions, right, then the system is known as consistent, because can solve lah. Can solve means consistent. Okay, so let me write here. This consistent means have solutions. So can be one solution or can be many solutions. Doesn't matter. As long as got solution, right, means consistent. Okay. So this occurs when all equations are linearly independent, so that you get a unique intersection point. Okay, second type, this one also demonstrated, infinite solutions. Okay, so you can see like this example, 2x plus 3y equals to 1. Then you take the first equation times 2, times minus 3. Then you get the second equation, correct or not? 2 times minus 3 minus 6, 3 times minus 3 minus 9, 1 times minus 3 minus 3. Can So actually, the 2 equations exactly the same. Okay, so what's the intersection space? A line, right? But is it consistent or not? Consistent, because got solutions, what? You see, got solution consistent already. Okay, but not all equations are linearly independent. Okay, as you can see here. Right? And also, another example. Okay, this one, you look at the system of linear equations here. Now you notice that the first equation, right, is 2 times of the third equation. Right? This one you times 2, you get the first one already. So actually the first one and the third one is the same plane. So because they are the same plane, then actually you just do planes what? So 2 planes intersect, must get a line. There, this is the line of intersection. Okay? So still consistent because got solutions, right? But there are infinite of them. There are infinite solutions. Okay? So how do you know you can get infinite solutions? In your Gauss-Jordan elimination, right, you are going to get a row with all zeros in the row echelon form. Okay, so later on we will see such an example where you get all zeros. Actually, all zeros means what? That means you got one row totally removed. One row totally removed means what? One less plane or one less geometry to intersect. Okay. Okay, then third one, no solution. This one I mentioned also. Okay, so no solution when you have parallel lines, right? They are not coincidental. That means they are not lying on top of one another. Okay. So when that happens, right, it can never intersect what? Then can never intersect, no solution. So no solution. So therefore you can see that this happens, right, when all equations are linearly independent, linearly independent. Okay, so what's the deal here? These 2, when you times minus 3, you get minus 6. Okay, no big deal. 3 times minus 3, you get minus 9. But on the right hand side, right, you do not get 1 times minus 3 here. So this equation cannot be formed by a constant multiple times the first one. Although they have the same gradient, but they don't have the same y-intercept. Okay, so you cannot say that you can take the first equation, multiply by some multiple to get the second one. So in this case, the 2 equations are linearly independent. They are not the same line, as you can see here. Okay, they are parallel, but they are not the same line. Alright, so when that happens, you do not have any intersection space, so no solutions. Okay, no solutions called inconsistent. It means the system is inconsistent. You cannot solve. Can? Okay? So the same thing goes for the 3D example. 3 planes parallel but not intersecting. If you look at the equations here, right, you understand why. Look at the first one, right? -2, 5, and 1 for the coefficients. The second one, the coefficient is just -1 times the first one. Right? You take a -1 times -2, you get 2 here, what? Correct or not? The same thing goes for the +5 to -5 and the 1 to -1. Okay, but the right hand side is not differing by a -1. Okay, so therefore these are 2 different planes. Then the same thing goes for the third one, right? These are 2 different planes, right? The third plane is different from the second, is different from the first. So therefore they can never intersect. So never intersect means what? Inconsistent, because there are no solutions. Okay? So how do we know? When you solve, now you will notice that you will have all zeros at the coefficient matrix, but a non-zero constant at the constant vector part. Okay, so let me demonstrate here. Okay, so like that. So this one row echelon form, right? Okay, so what you will get is something like that. You will get, this is a 0, but this is a 1 or 2 or whatever. So you see, how is it possible that 0x plus 0y plus 0z equals to a constant 1 or any other constant that is not 0? Does it make sense, what? How can be 0 equals to 1? So when you get something like that, right, then it's inconsistent. Okay, because 0 cannot be equals to 1. Or 0 cannot be equals to any number here that is non-zero. Can? Okay? So therefore, this is how we know whether we have which type of solution. Okay? So therefore, this is the summary. Right? It's a summary. Inconsistent means the system of linear equations is independent, right? But there is no solution. Okay? That's what inconsistent actually means. Right? When you have parallel geometries for your equations. Consistent means you have solutions. They can be unique or infinite. Right? If it's a unique solution, then it means that your equations are independent. Okay? If you do not have fully independent equations, then you are going to get infinite solutions. Okay? So therefore, basically just 3 types. So now we are going to jump into, right, a demonstration of each type. Okay? So it's supposed to classify. No need to solve, just classify. Right? If you can tell just by visual inspection, go ahead. Right? But if we can't tell, right, then we have to resort to the Gaussian elimination. Okay? So the first one, linear independence. Is the 2 equations linearly independent? Yes. Why yes? Because you can see this x, right? If you multiply by -1 to get this, but the y is not differing by -1, right? Correct or not? So therefore, this equation is obviously not the same as this equation in the sense that it cannot be formed by multiplying a constant multiple to either one of them. Okay? So therefore, this one, since rho 2 is not equals to some constant k times rho 1. Because if rho 2 is not equals to a constant times rho 1, then this implies that rho 2 plus k rho 1, right, cannot be equivalent to 0, okay, for k not equals to 0. Okay? So actually I should write like k2 lah. k2 rho 2 plus k1 rho 1. So what does this mean? Okay, for example, you can see that R2, if it's not equals to k some constant times rho 1, right? That means I cannot take some constant times rho 2 plus another constant times rho 1, sum them up and expect to get a 0 here unless all k's are 0. Okay, so let me write the alternative. Else, if, let's say, R2 equals to k1 times rho 1. Right, if let's say this is the case, R2 equals to k1 times rho 1, let's say which means from here you can write what? R2, or rather, R2 minus K1 rho 1 equals to 0, right? Correct or not? So you can see that from here, right? I just let. So this K1 is defined already. Okay, it can be 2, can be 1, doesn't matter, right? So from here, right, you can see that I can purposely go and choose a K2 such that this K2 R2, right, equals to positive of K1 R1. Okay? Or maybe let me write it more clearly. And that is, if I put a K2 here. Okay? So if this K2 R2 equals to K1 R1, right, then you're going to have this, right? Now when you have this, then you notice that this is going to be 0 for some non-zero K2 and K1. Okay? So if this is the case, right, then this is the condition for linear dependence. Okay? But it doesn't conform to this example in part A, right? Right? Okay, because it's not possible to take a multiple, right, times R1 to get your R2, or vice versa. Okay? Or vice versa. So let me add a K2 to this R2 for clarity. Okay? So therefore, if this is the case, then linearly independent. So because they are linearly independent, then it must be, it is consistent as well. Okay, why is it consistent? Because two lines, non-parallel. So therefore they will intersect. Unique solution. Okay, since the two non-parallel lines will intersect at a point. Is that alright? So that's for part A. So what about part B? Part B. Is it linearly independent? Just by inspection? No, it works. It works. Okay, you notice that the second one, this is 1/3 x, right? 1/3 x, let's say, how do I get a -2 here? I'm going to multiply by -6, correct or not? So if you take the first row, you go and multiply by a -6. You notice that 1/3 x becomes -2. -1/6 becomes +1. 2 times -6, you get -12. Then it's very clear that this is row 2 equals to -6 times row 1. Right? So which means this is telling me, right, row 1 or -6 of row 1 plus row 2, minus row 2 equals to 0, you know. So equals to 0 for what? For K1 equals to -6, K2 equals to -1. Agree, right? If you take the first one, you times -6, you get the second row, Then it is just -6 of row 1. If you go and take -6 of row 1, right, minus row 2, then you're going to get 0 everywhere. Correct or not? So therefore, notice that the K1 is -6, the K2 is -1, right? And you get 0 on the right hand side. So what does that mean? Not linearly independent. Because you can get some non-zero constants multiplied to each row, summed or subtracted, to get 0 on the right hand side. Okay? So therefore B is not linearly independent, or also called linearly dependent. Just different ways of saying the same thing. Okay? So when you have not linearly independent, then you can only have infinite solutions. Okay? That means actually the two geometries is the same thing, it's the same line. So therefore must intersect on a line. So infinite solutions. Okay? Because got solution, got solution means consistent. Any questions on the examples involving the two lines? Okay, the third one, let's look at the third one. I must tell you that for 3 equations, not so easy to tell. Okay? Because, for example, to get a third equation, it's possible that I take a constant times the first one, add to a constant times the second one. Right? Then I get maybe this coefficient. Okay, and this can apply for all 3, right? Including on the right hand side. So it will not be so easy to tell because you have many equations, you have also many variables. Okay, so for 3 equations and above, not easy to tell whether you get linear independence or not. Okay, so the way to find out, right, is to use the row operations. Okay, so we're going to go through the row operations here, right? So from here, okay, let me write, not easy to assess linear independence, so use row ops. Okay, so row ops, right, as usual, start from A, B. So this is your augmented matrix. So augmented matrix 1, 1, 1, 2, minus 5, minus 7, then minus 1, minus 1, 1, 1, 1, minus 1. Okay, so truth is, for the row ops, right, okay, I have already my coefficients 1 and 1 here, so that's nice. Okay, so I don't think I need to do any swapping of the rows. So I will just use the first row as is. Okay, so then row ops as usual, I want to make zeros for the first column. So I'm going to have row 2. This one looks familiar. Have I done this before? This for exact 2 minus 5. Hold on. It's actually, no, it's not this one. Okay, I've not done this before. So let's do it together. So to make zeros here, row 2 minus 2 row 1. Row 3 plus row 1. So we're going to get the first two zeros. Then minus 5 minus 2 minus 7. Minus 7 minus 2 minus 9. 1 minus 2 minus 1. Okay? Then the third row, minus 1 plus 1, 0. 1 plus 1, 2. Minus 1 plus 1, 0. Is that correct? Can? Okay, so this is good enough, right? You don't exactly get the row echelon form in the sense that you got all the ones here. Okay? But 1 or not 1 doesn't matter, right? Because how to make this a 1? I just divide by minus 7, if I want. Okay? How to make this a 1? Just divide by minus 2, divide by 2. Okay? So this is already the row echelon form. Good enough. So row echelon. Okay? Because I already my lower triangle of zeros. So if this is row echelon, right? Now you notice that. Ask the question. Do you have any rows with all zeros? The answer is no. Okay? Then what is the solution here? This is 2z equals to 0, right? Z equals to 0, So I can solve for z. Then I back substitute, I solve for y. I back substitute again, I solve for x. Correct or not? So which means unique solution. Okay? So let me write. No rows with all zeros. So the system of linear equations is linearly independent. And because it's linearly independent, all three equations, they can intersect. So unique solution. Any objections? Yes? How? Not possible. You want to make this all zeros? How? No difference. No, as in, it is not possible for me, right, to perform any row operations to make any of the rows all zero. Not possible. Okay? So once you get the row echelon form, you have entries, right, in the coefficient matrix, right, for all rows. That means you are having a linear independent system of linear equations. That means all three planes are here. They are different planes. They are uniquely different planes. Okay, so of course, to answer your question, better, right? I want you to try the same technique on part D. If you look at part D, right, it's not so, it's not obvious. So you have to do your row operations. I think after some operations, you will get something quite interesting. Okay? So I'll give you some time to try this one out, part D. And in the meantime, I will mark your attendance. Okay, so today is our tutorial. Alexander? No. Maybe it's in the other class. Aliyah, Emelina, Angelico, Sean, Jia Sean, Brian, Chen Chang, Zhen Yi, Ivan, Ivan Chow, Yang Eng, Emilia, Erwin, Yanjing, Zhan Yang, Dongping, Noritetsu, Javier, Joey Tang, Jordan, Kayla, Kevin, Ken Leong, Charan, Kieran, no. Dawson, Chen Ying, Jonathan, no. Kun Yong, no. Mac Kai Hin, Nikhil, Mohan, Azari, Danish, Irfan, Nitin. Is that correct? Nitin? Bing Jie, King Hong, Zixuan, Alexander, late for 1 hour. Fadila, Phoebe, Yan Heng, Sherwin, Benjamin, no. Raymond, Reese Tan Hong Yun, no. Rujiratana Lai, Junpang, Jerome, Sean, no. Sean Bryan, no. Justin, Hao Pao, Shi Hao Pao, Xia Jia Jun Ryan, Suhadi, Johannes, Wei Yan, Yi Zhong, no. Tianzhen, Trisha, a lot of new names, Trisha, Hong Tan, Yang Hong Tan, Xi Kang, Xing Zhi, Zotet, Zun Pin Wai. Okay, so, yeah.
So if we get all zero like that, right? But let's say we got fractions like this. Are we able to rewrite it as, for example, right? X plus 2y plus 3z equals to 14. Then we input this into the.
Can.
Okay.
Okay, so row ups, right? Yeah, so you can see that there are fractions here. Okay, so maybe it's better to just multiply by 2 easier. So this one, just 2 row 2. Okay, so 2 times row 2 lah, right? So 2 times row 2, then write down the augmented matrix. So you get 1, 2, 3 minus 1. Then this one will be, after you times 2, then you'll get 1, 2, 3 minus 7. Is that correct? Oh, sorry, it should be 14. Then this guy will be minus 3, minus 6, minus 9, 8. Okay, so this is pretty obvious. Because the second row and the first row, right, they actually have the same coefficients. So therefore, it is easy to get all zeros here. Because if you do row 2 minus row 1, and then you also do a row 3, right? Row 3 plus 3 row 1. So hence you are going to get all zeros for the lower 2 rows. Okay? But this guy is going to be 15 right here. Is that correct? Yeah, 15, right? Sorry? 15 over 2. But no, it's 14 minus 1. So it's 15 what? Then this is what? This is going to be 5. So you can see that this is inconsistent. Because for the bottom 2 rows, right, you get 0 equals to 5 and 0 equals to 15. Correct or not? All zeros here, but it is a non-zero constant. Okay? So that means this one is 0 equals to 5, right? And this one is 0 equals to 15. Cannot be what? Okay? So hence inconsistent. Okay? So in this case, are they linearly independent or dependent? Linearly independent, because you don't get all zeros. This is a 15, this is a 5, so it's not all zeros. So SLE is linearly independent, inconsistent. So once you have inconsistency, you have no solutions. Any questions? Yes. Yeah. Yes. Okay, so for this example, you can still see. That means you can still tell. Right? But in your tutorial or later on, you'll encounter examples whereby it's not easy to tell. But you can still end up with inconsistency or a full row of zeros. Okay? Yeah, this one quite easy to see because like the coefficients here and the coefficients here can match. Yes. Yeah, of course. I mean, if you like to work with fractions, right, you can leave in fractions in your row operations. Any other questions? Good. Okay, so you get more practice in your tutorials. So now we want to introduce Oh, by the way, maybe it's a good time to take a break before I go on to rank of a matrix. So let's take a break, 10:15.
So many for part D just now, right? So do we have to like write it down to prove it, or do we have to like show the process? Because it's unlike we have like tree, right? We have to write down like the SLE and everything we did, right? But this one has like
No. This one also can use row ops. You get the same answer one. This one also can use row ops. This
so
one can use row
in a
ops.
sense, it's better to use row ops, or do we just write down all this?
Oh, if you can see, if easy to tell, right,
Yeah.
and you can explain, then actually you can just write down. You can write down the argument and then conclusion.
But if you use row ops, wouldn't it be technically be faster as compared to-
Possible. Actually, very fast.
Because you write row ops, you just only you convert, then you can show that
Correct.
it's different. You can write a unique solution instead of just like writing everything, proving that it's equals to 0.
Correct.
And then say that it's actually linear independent, but it's not.
Correct. So row ops actually is the foolproof or rather mechanical way lah. You just do row ops, get a row echelon form. From there you can make your decision.
So in a sense, if we do this in like the paper format, right, it's better to use row ops.
Yes, it's the more so-called universally applied.
But we also need to explain that it's linear independent, is it consistent, or is it unique solution, or
No need.
no need, right? Just
You see from row ops from here from the row echelon form, you really can make your decision already.
or we just straight away we just say what is it consistent or not?
Correct. From
okay.
here, from the row echelon form, right,
Yeah.
you can make the
You can just straight away just say
Assessment.
the assessment really. Oh, okay.
Okay.
Thank you, Prof.
Right, so let's continue with the rank of a matrix. So this one is an introduction first. Later on, after topic 2, we will revisit this again. Okay, because after topic 2, you'll understand this better. So what's the deal with the rank of the matrix? The rank of the matrix is simply defined as the number of non-zero rows in the row echelon form. Okay, which also represents the number of linearly independent equations in the system. Okay, so for example, look at this part C. So what's the rank? Rank is 3. Can you see now? All 3 rows, you cannot get all zeros. So therefore, rank 3. So let me write down. So this one means rank 3. Okay, so rank 3 means what? Rank 3 means the planes demonstrated or the planes represented by each equation, they are independent. You cannot take any other two planes to combine to get the third plane. Not possible. Okay? So this rank 3 means all 3 planes all 3 planes are independent. Okay? So what about part D? Part D, you can see part D actually you notice that you still have 3 planes, because you don't get any what do you call it? You don't get anyone with all zeros as well. Okay? Can you see? Number of non-zero rows in its row echelon form. So you can see no all zeros. So the right hand side also makes sense. The right hand side must also be considered. Okay? So this is also rank 3. So this one, rank 3. You have parallel planes, but they are not the same plane. Okay? So therefore you still got 3 linearly independent planes. So this is rank 3. So let's look at part A. Part A is what? Rank 2. Okay, this one is rank 2. Why rank 2? Because the 2 lines are independent. You cannot take one line multiply by a certain multiple, right, to get the second line. Okay, so this one is rank 2. 2 lines are independent. Okay, I didn't do the row operations for this, but you can. Okay, you realize that you cannot possibly get a row of all zeros. Okay, but B is what? Rank 1. This thing is rank 1. Why rank 1? Because the second row is the same as the first row. Okay, now I just multiply by -6, right? You get the same form of the 2 equations. So therefore, there is in fact only one line. So therefore it's rank 1. So same one line. Okay, which means if you look at part B, right, you just take row 2, minus, or rather plus, row 2 plus 6 times row 1, you will get the second row all zeros. Correct not? So you only have the first row of non-zero, so that's rank 1. Because you only have one row. Okay? Okay, so that's the meaning of rank, right? And then the formal definition here involving the column vectors and whatnot, right? This one I'll explain again after we have covered topic 2. Okay? So, yeah, an exercise here, and okay, so this is straightforward. So you are supposed to solve, and then in this case, we are moving ahead to solve for the solution of a non-unique solution. Okay, so let's see how we do it. So this one actually quite straightforward. So because the first one, you can simply do a row 1 divided by 2. So if you do a row 1 divided by 2, then your row ops, your augmented matrix is going to look like 1, 1, 1, 1. Okay, and that is exactly the same as the last row. So you can see that it is a linearly dependent system already, just by having one operation. Okay? So from here, try to get your row echelon form. So you do a row 2 minus 2 row 1, and you do a row 1, or rather row 3 minus row 1. So let's see how we solve after we get the row echelon form. So hence the last row is going to be all zeros, and then the second row is going to get 0, then this is a minus 5 minus 2 is a minus 7, minus 1 minus 2 is a minus 3, then 7 minus 3 is going to be a, 7 minus 2 is going to be a 5. Okay? So you can see that after one, or rather after 2 row operations, right, you get your row echelon form ready. Okay? So I think most of you are comfortable with that. We can do our back substitution. And you can see that because you have one last row of all zeros, right? So this is telling you that the SLE is not linearly independent. Okay? So let me write. So the system is not linearly independent, but because you do have consistency, meaning to say you don't get, right, 0 equals to 5, for example, no such thing. 0 equals to 0, perfect, no problem. Okay? Not linearly independent, consistent, or is consistent. But because effectively you have rank 2, right? Rank 2, and you have only 2 effective planes, 2 independent planes. 2 planes intersect with a line. So that means infinite solutions. Okay? So rank is 2. Okay, so I think the assessment of the solution type and the rank is done. So now we are going to solve. Okay, so of course the last row nothing to solve. 0 equals to 0, nothing to solve. So you can start from the second row. So the second row is going to give you what? Minus 7y minus 3z equals to 5. Can? So therefore, you can isolate whichever variable you want. Doesn't matter actually. Okay? But just to follow my answer here, I isolated the z variable. Okay? So I'm just going to do that. So z is equivalent to what? So the minus 3z you bring across, then after that divide by 3 throughout. So you're going to get a minus 7y minus 5 divided by 3. Okay? So that's isolating my z variable. Right? But this is z in terms of y. Then what about the first row? The first row also must do. Okay? So from the first row, I'm going to get x plus y plus z equals to 1. Okay? So I can also isolate z here. Right? In fact, from here, right, because I want to get my z in terms of x, later on I will explain actually what the solution represents. Okay? But you notice that this thing is a z in terms of y. Now from here, I want to get z in terms of x. Is it possible or not? Yes, it's possible. Why? Because z has been expressed in terms of y here already. So I can substitute this into this, right? To get rid of the y term. Alternatively, I can perform row ops here. Okay, I can perform row ops here because this is my row 2, right? And this is my row 1. So what happens is that if I do row ops, so if I do, so you can continue to do row ops or you can solve here as well. So you notice that I want to get rid of what? I want to get rid of y, right? So what do? I just take 7 of row 1 plus row 2. Okay, row 2 put in green color. Okay, 7 of row 1, because so I can get a 7y here. Now I go and plus this minus 7y. So obviously the y term disappears. Okay, so let's see what you're going to get. So you're going to get 7x. Then the y minus y disappear. Or rather, 7y minus 7y disappear. Can Then this is what? 7z, right? Plus minus 3. So it's going to give me 4z. So this is going to be 7 plus 5. Is it 7 plus 5? Yeah, 7 plus 5. So it's going to be 12. Okay? So now I isolate the z. So z is going to be what? It's going to be minus 7x over 4 plus 12 over 4. But 12 over 4 is just 3, what? So this is your answer. Okay. So you notice that you have two expressions of z. This is the first expression in terms of y, and this is the second expression in terms of x. So if you combine the two expressions, right, the solution is z equals to, you can write down the y expression first, then followed by the x expression, or vice versa, doesn't matter which is the order. So this is the full solution. Okay, I'll explain what is the meaning of this solution. Okay, so let's define the solution. So remember, 3 planes, right? Then you have variables x, y, z, right? So which means that it is in 3D coordinate space. So this is your x, y, z. So what is the green line representing? Now the green line is representing a line projected on the z-y plane. Now look at this part. Because it says z equals to minus 7y minus 5 over 3 ma. I mean the gradient is minus 7 over 3 lah. So maybe the line looks something like that. Can Okay, that's the green line. Okay, it's projected onto the zy plane. Then what about the pink line? The pink line is on the zx plane, correct or not? So therefore, maybe the pink line looks something like that. So how is it possible that you get projection onto the zy plane, giving us the green line, projection onto the zx plane, giving us the pink line? That means your solution must be a line in the 3D space, right? Maybe looking something like that. This is the solution. This is the intersection space, the intersection line between all 3 planes, or effectively 2 planes. Because the rank is 2 ma, only got 2 planes. So 2 planes intersect at this black intersection line, right? So these are projections. So this one is like projected onto the zy plane, looks something like that. And this one is another projection. So the truth is, you can express isolating z. Some people like to isolate y. Then some people like to isolate x. Doesn't matter. Okay, you'll still get the equivalent form. So let me write. This is the intersection line between the 3 planes. So actually it's just 2 lah. Any questions? Because this one maybe a bit messy. Correct. If the rank is 2, which is less than the number of equations, right, then you get infinite solutions. I repeat that again. If the rank is less than the number of equations that you are given, right, you will get infinite solutions. Because this represents that if the rank is 2, less than the number of equations, right, that means actually you are looking at like 3 geometries, hoping them to intersect at a point. But actually, you only get two independent geometries. That means like two planes. So two planes must intersect at a line. Then a line, right, is considered infinite solutions. Is that right? So is it possible that the solution is a plane or not? Possible. If I give you all three planes being the same plane, right, then the solution space is a plane. No? That means the solution is the plane equation itself, because all three planes actually the same thing. Yeah. Plane is flat, just like line. So it must be straight and flat geometry. The same thing goes for 4D and 5D and above. Just that we cannot imagine. Any other questions? Okay, good. Can sorry? No. If it's 4 equations, if I give you 4 equations, I got W, X, Y, Z to solve. You must get rank 4 to get unique solution. Can Okay. Now I'm going to have an introduction to mathematical modeling. Actually, probably not the first time that you are seeing this, because in your circuit theory, you have effectively performed mathematical modeling as well. Okay? Because what you did was apply KVL, KCL, right, to some engineering problems such as a circuit. Then after that, you try to represent them in the so-called matrix notation, right? And then you write down the supposed solution. Okay? So this is a skill that is very important and essential. Okay? Because typically, what we want to do these days, right, is we want to represent the problem in the computer and then use the computer to simulate. And we can do the design in the computer as well, such that we get a more or less optimum design. Okay? Then after that, we will implement the actual design in the real world. Okay? So we always start with the real world problem, then interpret and derive the mathematical model. Then in the mathematical model typically entered into a simulator in the computer. Okay? Then after that we solve, right? We get the mathematical solution. Then after that, after we assess the solution, right, we will need to interpret and deploy to test out whether it can solve our problem or not. Okay, so this is a very high level and brief flow chart introduction to the mathematical modeling. Okay, later on in chapter 3, I think it's topic 3, you will get a more in-depth understanding, because we will be delving into how to derive the mathematical model. That's the big part of Math 2. Okay? So this is first example, at least for Math 2, okay, on this economic model, which actually makes use of our row operations or Gaussian elimination. Okay? So just an introduction, don't have to worry too much, because the actual model can be horrendously complicated. Okay? So it's invented by this economist, right? You can see his face here, right? Wassily Leontief. Okay? Later we talk more about him, right? But now what he did is that, right, he go and invent or derive a math model that describes the interdependencies between various industries in an economy. Okay, and his aim is to analyze or assess, right, what is the ideal amount of production for each industrial sector. Because as you know, right, our industry is all interconnected lah. Okay, let's say you want to buy your phone, right, your handphone. Okay, but your handphone needs chips. So therefore, you got to look at the chip production, right? TSMC, for example, right? If you are holding, for example, iPhone, okay? Then to make a chip, then you need to look at the raw material, for example, wafer, as well as the rare earth metals, okay? So you can see they're all interdependent, right? So he aims to write down the interdependency in the form of equations. Then after that, solve those equations to identify the ideal amount of production. Because if the production is above the ideal amount, then of course it's going to cascade. The effects are going to cascade throughout the whole industry, right? And it's probably going to result in, like, for example, a downturn or the demand being so-called too high, such that the supply cannot satisfy. So it can be all sorts of actual economic circumstances. Okay, so this is what he's trying to do, trying to use math, right, to analyze the economy. Okay, so let's look at a simple example. Now you have a simple economy that has two industrial sectors. Let's say just produce electricity and water. So they are necessities, like human needs. So it is known that to produce electricity, water is needed. Why water is needed? Because how we produce electricity these days, usually using steam turbines. Okay, so how to operate steam turbines to produce electricity is that you got to heat water. So you heat water, produce steam, then steam go through the steam turbine connect to generator, then generator will spin, right, and then produce electricity, usually in the form of alternating current. Okay, I think that's what we all know. So now, in order to produce electricity, the input, water is needed. But to produce the water, electricity is also needed, you know. Because to produce water, right, let's say for example, in the Singapore context, you need to maybe do desalination for a portion of the water, our new water, okay. So desalination means what? You need to pump the water, right, at high pressure through your reverse osmosis filters. So therefore, you need to operate pump. Then pump is what? Pump is requiring electricity. Okay? So to produce water, electricity is needed as well. But not only that, so that means you can see that electricity and water production, right, they are interdependent. Okay? But not only that, to produce electricity, some electricity is also needed because you need to operate your lights and equipment, right, at the electricity plant. Okay? And to produce water, some water is also needed, for example, to clean equipment. So therefore, in a nutshell, the production of each sector is dependent on itself and the production from other sectors. So if you have two commodities, two production items here, is already forming two equations. So what are the two equations? Okay, so let's delve into a more concrete example. So let X be your electricity output. Your Y is your water output. Now, to produce 1 unit of electricity, let's say you need 0.2 units electricity and 0.4 units water. So this one we just mentioned, right? If you want to produce electricity, you need electricity. But you also need other production items. Okay? So therefore, look at this first part, right? Is at the first row. Can you see this X, okay? Then to produce X, right, the input to X is 0.2 units of X. Then the input to Y is 0.3. So where is this 0.3 coming from? 0.3 coming from the production of 1 unit of water. Okay, so 1 unit of water, let's say you need 0.3 units of electricity and 0.1 units of water. So therefore you can see the 0.3, right, appearing here. You can see input to Y, okay, because Y is your water, right? So you need 0.3 units of electricity. So this is the 0.3. Can, okay? Then also water output, right, is Y. So you need 0.4 units of water. That's here. Then, but you also need 0.1 units of water, let's say to wash the plant and whatnot. Okay? So what about other demand? Of course, you don't just produce the electricity and water to serve the production, what? You have to serve the community, that's the human need, what? So therefore, human needs 20 units of electricity and 32 units of water, let's say. Okay? So this is a table. So after we tabulate this, right, because all these values, right, you can get from the industry in the actual economy. Okay? That's why we have our industrial survey, consumer survey, as well as business surveys, okay, done by our government departments, right? So now, can we form the equations or not? The answer is yes, okay, because once you have the table, not too difficult to form the equation already. So the output, right, X, electricity output, must be 0.2 times of X. That means 20% will go into the electricity production. Okay? Then plus 0.3 of Y. You see 0.3 of Y. You see here. Then, but you need to satisfy the 20 units of consumer demand. So it must be plus 20 here. Okay, so the production equals to consumption. input must be equal to output. Can production equals to consumption. Production is here. Okay, doesn't matter which lah. Right? Production must be equivalent to consumption. The same thing goes for the water. Can so two equations, two unknowns x and y. Now of course the solution is easy, right? We just use row ops and whatnot, right? Simultaneous equation, substitution. You can get x equals to 46, y equals to 56. Okay? So this is a very simple problem involving only two commodities. Okay? But of course, this thing like chicken feed, right? So what this guy did, right, is he went to model the US economy in, or rather before 1973, that is comprised of 500 sectors. Because got many things to produce what? Not just electricity and water. So imagine he got 500 equations. So his matrix is 500 by 500, which is actually not a big deal these days. But last time, 1973, right, without like GPUs, it's a big deal. Okay? Yeah, so he go and solve it. Of course, he don't solve by hand, right? He also use computer, but at that time the computer quite not as fantastic as today's computers. So therefore, he won the Nobel Prize in 1973. Okay? So if you think back, actually quite ridiculous. Wow, use row operations to solve linear equations can win Nobel Prize, right? Which is what you're learning now, which is what you have just gone through. And it seems like quite simplistic. Okay? But of course, we are standing on the shoulders of giants, right? Why we learn this? Because it has been effectively applied before in many areas. Okay, including economic analysis. Okay, yeah. So this is just a story to tell. The good news is you will not be tested on the economic model here. Okay, you won't be tested on the economic model because the realistic model is actually quite not possible to solve by hand. Okay, but you will be tested on mathematical modeling of other real-world scenarios, other real-world examples, as you can probably identify from your tutorials. Okay, so usually your tutorial, the first few questions like theoretical understanding or practice. Okay, so after you have done with that, right, then the last few questions typically involving mathematical modeling. So how to read and interpret the model and write down the equations will be part of your assessment. Okay? Yeah, usually won't be too cruel in the sense that we won't ask you like 120 mark question, right? Derive and solve. Okay, because if you derive the wrong system, then that's it for you, everything wrong. 20 marks gone. So it won't be that cruel. So typically it will be part A, maybe 6 marks, derive. Show that you can get this system. If let's say you cannot get, okay, it's fine. Maximum you lose 6 marks. Then after that, right, the solution comes in the part B and C, for example. Okay? So if you are not good with interpretation, then at least be efficient or be proficient, right, with the solution procedure. That's it for topic 1. Okay? Any questions? If no, then we can call it a day, right? Next lesson, which is tomorrow, we will be looking at tutorial 1 questions. So if you have not attempted the questions, please attempt first. Okay, so I'll see you tomorrow.
The 3D graph, right? The intercept will be, it's just considered this line, here and here. Because just now you draw the graph.
Correct.
So it will just be here.
Planes only, right?
Yeah, of course this one is not intercept. But if I change it to like,
Then different.
this one doesn't intercept.
So
But you
what
say
is
you got 3 planes, right?
Very good. So you see, just now you changed this number, right?
Yeah.
You attempted to make one of the planes different, right?
But I want to make, let's say all 3 planes start each other. Right?
Still cannot see it.
See what? You see, okay.
How can they
So
allow?
by right, if all 3 planes are independent, then what's going to happen is that, right?
If you divide this by
your
3,
three
then the
planes
same
will
line.
intersect at a point.
That
then
will
like
be the intersection also.
the
Intersection
question
point
normally
lah,
not like
which is
that,
solution lah.
But let's say in the
Like,
tutorial,
let's say
you
just
got
now
to
the
draw
other
out.
question like this type.
No, you
What's the
don't have to draw.
solution?
Okay,
Because if I
just
like
now.
4D and above, right, 3D is not so
Just now
easy
is
to draw.
below.
So, okay, so what you did here, right, was to change the last number, right? Correct enough. Then you notice that you have parallel planes,
take a
right?
look at this.
But these two planes can never intersect, right? Correct enough. So that means, actually,
you
you
can
have
tell
this
that your
system,
gradient is
you
different.
can go and try.
But you cut the same
you are going to
axis,
get
so it's like an X.
inconsistent.
So this is one unique solution, right?
No.
Independent, one unique
Inconsistent.
solution. This is you
When you say two
times 6.
intersections, it's like you are saying that, oh, okay, red
It's the same line,
intersect with
because this
blue
equation
plane.
reduces the same
Then
line.
green intersect with blue plane.
No,
So
I
you got
didn't
two
know.
lines, right?
Times again.
But
Yeah,
then
it's the same
you see,
line. So this
this
is
line
infinite
cannot
solution.
satisfy the
No, I
other
didn't.
line. One of the
Times
lines,
6.
right, cannot
Negative six.
satisfy
Yeah, negative
the other
6.
plane.
And for
Right
this
now.
one,
So that means when you look for solution, it must be satisfying
So
all equations.
they say 3 line a bit harder to see. You
Ah,
cannot see,
so
right? You
in
must
this
do
case,
your
I
row.
think
Yeah, that's what I was thinking about. I was thinking about 3 line. How we use it.
Then in
you
your
rush
row
lor.
ops, if
If
you
your
do,
two line can see good lor,
you will
but
get
then you might
0
want to do it
equals
to
to some
confirm.
non-zero number.
Prof, sorry. The row echelon, right? Like he said, he asked a question just now. So if let's say my last row is okay, 0, 0, 0, 0, like all 0. Or my second last row is 0, 0, 0, and then my constant is a non-zero constant.
Oh, inconsistent.
Inconsistent, because your last row is disregard, right? Doesn't matter, right? Is it because your last row you disregard because it's all 0 anymore? So you lose one plane less, one less plane.
Correct. If you lose the last plane, then effectively you got 2 planes. But in that 2 planes, one of the plane cannot intersect the other.
So it's
Because you get 0 equals to some non-zero constant. So effectively it is inconsistent.
Prof, can do my attendance.
Oh,
Yes.
you late
Huh? Yes. No, I'm supposed to be the other class.
Jerome, right?
Yeah. I'm supposed to be the
You
other
can come
class.
to earlier class, like, no problem, right?
Yeah, you can come to any of the 2 classes because the space very
Actually, I
big.
thought that. Yeah, actually, I thought
The
that was.
space can fit everybody, right? You're not tired to teach the same thing twice, man.
Well, that's what they plan.
The space can fit everybody, right? You see it.
Okay, but for unique solutions, right, it just means only at that point, then everything is linearly aligned.
Huh?
Okay, so let's say I have a unique solution. What does it mean in terms of?
Oh, that means that point, right, will be on all the geometries given in the equations.
That point will be on
All
yeah.
geometries.
So will
Let's
this
say-
ever even be useful at all? Like, let's say you have to do
Useful in what sense?
application based on.
Useful?
Like how? Like what's the point? Wait, so you just find the perfect, like let's say the perfect mixture of a certain stuff.
Correct.
Oh, before it. Oh, okay.
Yeah,
okay.
that is possible, the so-called perfect mixture or perfect combination, right? Is not unique. It's possible.
How does it work then?
Because it's possible that, let's say for example, if you got a solution of a line,
Yeah.
there is infinite solution. So which means to say what? Which means to say, let's say you got this equation. Let's say you got this equation as your solution. So what does that mean? It means it's not unique, but one of, or rather, any 2, okay, so in this case, right, it will be 2 of the variables will be dependent on the third one. So if I change x, then you notice this y is going to change.
Yeah, correct.
Then if the x change, z is going to change also.
Yeah, correct.
So which means this could be the so-called ideal mixture or ideal combination. So that means you have a freedom, you have 1 degree of freedom, right, to get vary one of the variables. That means if you choose one particular
then
value
you
here,
affect
right,
the other, then you
then
affect
the
the
other
other.
you have to choose
Oh.
the appropriate one according to the equation.
Okay, I get it. Alright, then the second one is the infinite solution. Can you explain again why when the rank is lesser than the number of equation it is infinite?
Oh, because if the, let's say for example, if it's full rank, full rank means 3 equations, let's say in this case. So if it's full rank, that means your 3 equations will be independent. So therefore, they will intersect at a unique point.
So
Correct or not?
3 point. So they're all independent. They will say yeah, correct.
Correct or not? Then it will intersect at a unique point. But if you take away one plane, any one plane,
the whole plane they're all intersecting.
that means the intersect along whole line already. Because two plane like that intersect. Then the intersection is a line.
Intersecting already, so the whole plane is line.
The whole plane intersect, 2 planes intersect at the line.
Oh, 2 planes intersect at the line. Wait,
Yeah.
let me imagine it. Okay.
Two planes confirm intersect at a line one. No man.
What do you mean by two? It's more of the English that I'm a bit confused. Two plane intersect at the line.
Two plane.
Yeah.
This is one plane.
Good. Yeah.
Then we have another plane.
Oh.
So where's the intersection? The intersection maybe here.
Oh, okay, I got it. I got it. So that. Okay. He's cutting through.
Yeah,
the
two
water.
planes intercut each other.
Okay.
So the intersection space is a line. So what does that mean? That means if you, okay, let's say in the system, right, let's say you do 3 planes. 3 planes means if you have full rank, that means all 3 planes they are independent. Then you can intersect at one point. Because if I add another plane, now this is the intersection, if I add a third plane, then the intersection is
It's guaranteed.
is here guaranteed to be on the red plane as well already.
Yeah.
Then become 1 point.
Oh.
If I remove any of the planes, then become a line intersection.
Oh.